In this section, we're going to come up with an expression for intensity as a function of the angle for a single slit. Now, previously, we treated the single slit as effectively two different points. We chose a point at the center of the slit, and we chose a point at the edge of the slit, and tried to find out where the path length difference either produced constructive interference or destructive interference. In reality, this slit should be treated as an infinite number of tiny little points, tiny sources of electric field, which are going to propagate their own little wavelets to the screen and solve for that pattern as it forms on the screen, take the square of the electric field to then find the intensity. So unfortunately, this means that we have to rely on calculus. Now, again, we're thinking about the contribution from each of these little infinitesimal points, these infinitesimally small sections on the slit, contributing this electric field dE, okay? It has some intensity, which is spread out over some area. We're not going to worry about this because, we want more of an expression about how the intensity in the electric field changes rather than an exact value here. Now, you can see here we have cosine kr minus omega t. This is typically what we expect for a propagating wave, plus we have this little phase difference here. Now, here's the key. This phase difference is due to the different locations on the slit. So if we go from 0 in the y direction to negative a over 2, okay, or we go from 0 to a over 2, we're moving in the y direction, and the phase is going to be slightly different due to this different location. We did this with 2 points before. Now we're going to do this with an infinite number of points. That phase difference is going to go by k. K is 2 pi over lambda times sine theta times dy. So what we need to do here is we need to integrate over all the points, okay? From negative a over 2 to a over 2. We need to integrate over all these points. And if you take the integral of cosine theta, we know that we get sine theta. So when we do this, however, we actually have a function here. We're going to integrate this, okay, over all of dy, and therefore we are going to get a different expression. Okay, here's our integral right here. We're going to integrate, and you notice here that I have k sine theta a over 2 in the numerator and k sine theta a over 2 in the denominator. So I'm integrating this expression right here, and now I have this new expression, basically sine of some function, we'll call this beta later on, divided by beta, okay? Now, we can separate this into two different parts. We can separate it into the oscillating wave, okay? So this is going to oscillate as a function of time. This is going to oscillate as a function of position. But basically, if we take the time average of this, this is going to be, basically cancel out to be about 1/2. But this is what we're interested in right here, because this is our function that is going to vary as a function of theta. So our electric field is going to, I should probably have primed this, equal to some, maximum electric field. Again, it's oscillating with respect to position and time, but here is where my diffraction pattern is going to come from. It's going to come from this right here. This has an angular dependence, and therefore, this is what I'm interested in seeing, how it produces this pattern right here. So once again, we see intensity, and intensity is going to be equal to the electric field squared divided by the speed of light divided by the permeability of free space. Essentially, the intensity, which this is what we're interested in, is going to be proportional to the electric field squared, the time average of the electric field squared. So again, this thing's oscillating with respect to time. So we just want to sort of, take the average of this So when I simplify this, I'm going to say beta is equal to Ka sine theta over 2, just to simplify the expression. And we see that on average, the electric field goes by this sine beta over beta. Now, this expression right here is sometimes known as a sinc function, SINC of beta, which looks very much like the diffraction pattern that we saw before. And again, yeah, we've got all these other terms here, but we're not interested in these terms that are varying very rapidly, okay? We're interested in the larger terms, which are going to be used to give us our intensity pattern. So this is what a sinc function looks like. This is what a sine beta over beta looks like as a function of beta. And we can see how it oscillates and slowly damps out as beta gets larger and larger. It's a maximum at 0. And probably the first thing that you'd say is, wait a minute, isn't sine of 0, 0? Well, it is. But look at this expression right here. It's sine of beta when beta is 0, and we divide that by 0. At small angles, sine beta goes to beta. Beta divided by beta, 0 divided by 0 goes to 1. Okay? So at the center right here, we have our maximum value. And again, the oscillation comes from the fact that we have this sine function, but we're dividing by beta, so it's getting smaller and smaller and smaller. And that's exactly what we see. Okay, so let's take a look at not the electric field, because the electric field is not what we see. It's going positive, negative, positive, negative. We want the square of the electric field because the intensity is proportional to the square of the time average electric field. Okay. Oh, by the way, if you really want to get into some complicated math, there's something called a Fourier transform. And with Fraunhofer diffraction, if you take a function such as, let's say we have a slit right here, which has a given intensity between negative a over 2 and a over 2, okay? And we put this through a Fourier transform, guess what? We get out the sinc function. So basically, by taking whatever aperture you have, putting it through a Fourier transform, your output becomes essentially the time average electric field. I know I'm doing a little bit of hand waving here, and it's not exactly that case. But basically, we are saying that the intensity is proportional to the time average electric field. Okay, it is an electromagnetic wave. I do understand it's oscillating, but if this is visible light, it's oscillating at what, 10 to the 14 hertz? It's oscillating so quickly, it really doesn't make a lot of sense to, consider that. It makes sense to consider the time average. But again, here's the pattern that we get. We get that the intensity is equal to some peak intensity. Here I've set the peak intensity to 1, so I0 is 1, times the square of the sinc function. And you can see that when we square it, its value can only be positive, and the central peak is even larger compared to some of the other fringes. So here's our central bright fringe, dark fringe where it goes to 0, first bright fringe on either side, dark fringes, and so on. And if I superimpose our diffraction pattern, this is what it looks like next to the intensity plotted as a function of angular distance. And again, remember what this beta means. Going back, we made a substitution and said that beta, okay, I have to go all the way back here, is Ka sine theta over 2. So for small angles, beta is really proportional to the angle, because in the small angle approximation, theta is approximately sine theta. Okay. Also, beta is inversely proportional to the wavelength. So as the wavelength gets smaller, this value of beta gets larger and larger, which makes the function oscillate faster, which would make the fringes closer together. And A is the width of the slit. So the smaller the slit gets, the smaller beta gets, and that spreads the function out.